When it comes to lightning protection, it helps to think of the power system as principally two distinct structures. The grounded components, represented by the towers and ground conductors, and the floating components, represented by the phase conductors. These two distinct structures are separated by the line's insulation. When lightning strikes the grounded components, the tower experiences a sudden increase in potential. In ideal circumstances, this increase in potential doesn't cause any problem and the lightning current is safely conducted to ground. However, in some cases, like situations of poor grounding or very large lightning strike currents, the increase in the tower potential can exceed the line's insulation withstand. This is a backflashover. It's important to note that during the lightning impulse, the resulting stress across the different insulators is not evenly distributed. The lower insulators typically experience more stress as compared to the upper insulators. This is in part due to the different electromagnetic coupling factors between the different phase conductors and the grounded components. If you have a floating conductor in proximity of an energized conductor, a potential will be induced onto the floating conductor that is of the same polarity as the energized conductor. The closer the floating conductor is to the energized conductor, the greater the induced potential. Since the phase conductors are floating, when the grounded conductors are energized by a lightning strike, a potential is induced onto the phase conductors which is of the same polarity as the energized ground conductors, including the tower. This has the effect of limiting the potential or stress across the insulators. This is one reason why the upper phases are generally more resistant to backflashover. Noting this coupling effect led to consideration of the underbuilt ground conductor, an additional ground conductor that is placed below the phase conductors. It can be shown that the effect of the underbuilt conductor can reduce backflashovers by a factor of between 2 and 3. However, there are some drawbacks, the effect on ground clearances being perhaps the most obvious. In recent years, Lightning Electrotechnologies has developed a novel, more accurate method for calculating the effect of conductor height on ground wire corona and its subsequent effect on surge impedance. This makes it possible to find a location on the tower, a sweet spot which results in optimized coupling factors to all phase conductors, thus minimizing stress on all insulator strings simultaneously. The effect is to reduce backflashovers by a factor of 10 or more as confirmed by EMTP calculations. The only thing that would be more effective in preventing backflashovers would be to put an arrestor on every phase of every tower, which would be much more complicated and far more expensive. Additionally, unlike line arrestors, the embedded conductor cannot be the cause of a pollution flashover. The embedded ground conductor can be used on compact towers where arrestors may be difficult to install. The price does not increase with increasing system voltage. The embedded ground conductor has a longer lifespan. During the same time period, you may need to replace the arrestors, maybe more than once, in future currency. Also, critically, the dielectric clearances pose no problem. Using an example from the IEEE paper, a 245 kV tower with the following specifications under intermediate wind and with a swing angle of 40 degrees, the embedded ground conductor phase conductor clearances satisfy IEC 71-2 requirements for conductor structure gaps. The embedded ground conductor, a low-cost, maintenance-free solution to backflashovers.